Good morning, everyone. Today we have Mahesh from IIST Thiruvananthapuram with us to discuss problems on functions of several variables. This session is in continuation with the previous session where the necessary concepts were introduced. I hope today he may discuss and concentrate more on problems. I express my sincere gratitude to Mr. Mahesh for joining with us. I welcome all of you to this program and hope that today's sessions will be fruitful to all of you. Thank you all. I request Mahesh to handle the problem solving session now. Thank you.
Yeah, thank you, sir. I will directly go to this section. So I have to. So first, I will just recall the things what I have discussed last class. So let me quickly recall those things. So first, I have discussed something called limit and continuity. So for that, I introduced the concepts limit xy tending to x naught y naught f of xy. So what actually it means, we have to consider all the curve passing through the point x naught y naught. Then we will approach along each curve limit xy tending to x naught y naught. And if all those values are equal, we say the limit exists. And this is the and this one is the notation for that limit. Then we have discussed something called continuity. The continuity is limit xy tending to x naught y naught f of xy is equal to f of x naught y naught. So the function is had to be continuous at the point x naught y naught if this limit value should be equal to f of x naught y naught. Okay, then that we can understand by using sequence. Suppose we have that continuity at x naught y naught, how we will understand by sequence. For every sequence x and yn converges to x naught y naught, f of x and yn converges to f of x naught y naught. Then we say f is continuous at x naught y naught. Then I have introduced something called a uniform continuity. So the uniform continuity, how we have defined, if you consider any two sequences x and yn and a and bn such that their distance goes to 0. So you have to pick any two sequences in which their distance goes to 0, then it should implies f of x and yn minus f of an will goes to 0. This is the definition for uniform continuity using sequential idea. Okay, then I have introduced partial derivative. So the partial derivative at x naught y naught, this is the formula for finding the partial derivative with respect to x at x naught y naught. Limit h tends to 0, f of x naught plus h, comma y naught minus f of x naught y naught by h. This is the partial derivative at x naught y naught. Similarly, I have the partial derivative at y, x naught y naught with respect to y, dou f by dou y at x naught y naught. This will be the formula for that. So these all things we have discussed in the last class. So I just quickly recall this. Then the important things to remember is the first one is for continuous function partial derivative need not exist. This is the example I have discussed that time. F of xy is equal to square root of x square plus y square, and we have seen that the partial derivative at 0 0 and for both the partial derivative does not exist. Dou f by dou x at 0 0 as well as the dou f by dou y at 0 0 both are does not exist for this function f of xy is equal to square root of x square plus y square. Similarly, the converse of all this also not correct, or I cannot say the converse. The existence of partial derivative need not implies the function is continuous. So this is the example I have given there. So for this function, both the partial derivative will exist at 0 0. That is fx at 0 0 and you can see, yeah, fx. Fx at 0 0 and fy at 0 0 both exist. Okay, but function is not continuous. We have seen this function is not continuous. We can approach 0 0 along two different curve, y equal to x, y equal to 2x. This example we have already discussed. Okay, then I have introduced something called directional derivatives. So this is the definition for directional derivative. So what we are looking the directional derivative in the direction of some unit vector. So we have to consider the unit vector u1 u2. Unit vector means u1 square plus u2 square is equal to 1. Then the directional derivative is defined by this way: du of f at x naught y naught is equal to limit t tending to 0 f of x naught plus tu1 y naught plus tu2 minus f of x naught by t, where u1 u2 is the given direction, and we are evaluating the directional derivative at the point x naught y naught. Then we have seen the directional derivative in the direction of the vector e1. E1 is the standard unit vector 1 0. So we are looking the directional derivative vector in the direction of e1, that is nothing but the partial derivative with respect to x at x naught y naught, and the direction in the direction e2 is nothing but the partial derivative with respect to y at x naught y naught. And here also I just mentioned some important things to remember. So that is the important thing is this: the directional derivative of f at x naught y naught, that is denoted by du of f at x naught y naught, that need not be equal to del f at x naught y naught. I have given one example. This is the example. I have seen all the directional derivative at 0 0 exist, but du of f at 0 0 is not equal to del f at 0 0. We have seen this del f at 0 0 is 0, but the du of f at 0 0 is not equal to 0. So that, for all direction it will exist. Okay. This example we have already discussed. And now I will pose some questions. This also we have seen there. Suppose all directional derivative exist at 0 0, is that implies f is continuous? So the answer is no. For this function, so the same example I have taken, for this function is not a continuous function at 0 0, but directional derivative du of 0 0 exists for any unit vector. So all the directional derivative exist, that does not imply function is continuous. And the other question I can ask this: so whether the continuous function always have a directional derivative, or there exists a continuous function in which no directional derivative exists at some point. So this is the example for this. This is a continuous function, but its directional derivative does not exist. So this also we have seen. And then I have gone for the definition of derivative of a function of two variable. So what do you mean by the derivative? So let f from D subset of R2 to R be a function, and x naught y naught is a point in D. We say f is differentiable at a point x naught y naught if there exists a alpha beta belongs to R2 such that this relation holds. So this alpha beta is called the derivative of f at x naught y naught. So limit hk tending to 0 0 f of x naught plus h y naught plus k minus f of x naught y naught minus alpha h minus beta k by square root of h square plus k square is equal to 0. So if there exists such alpha beta satisfying this relation, then we say f is differentiable at the point x naught y naught, and the derivative at x naught y naught is nothing but the vector alpha beta. Okay, here also I mentioned some important things to remember. Suppose f is differentiable at x naught y naught, then this alpha we can find. The alpha is nothing but partial derivative with respect to x at x naught y naught, and beta is nothing but partial derivative with respect to y at x naught y naught. So fx at x naught y naught and beta is fy at x naught y naught. Then the derivative df at x naught y naught will be nothing but the del f at x naught y naught. So that is fx at x naught y naught and fy at x naught y naught. So this is the derivative. Suppose f is f from some d subset of R2 to R. Suppose that function is differentiable at x naught y naught, then its derivative nothing but del f at x naught y naught. Okay. And I have mentioned some properties of differentiable functions. The first one is a very differentiable function. If f is differentiable at x naught y naught, then f is continuous at x naught y naught. And the second one is if f is differentiable at x naught y naught, then all the directional derivative will exist at x naught y naught, and du of f at x naught y naught will be equal. So in order to become the equality, we need function has to be differentiable at x naught y naught. Then only we can write du of f at x naught y naught is equal to del f at x naught y naught. So that means if you want to find the directional derivative of a function, sorry, del f at x naught y naught dot to u is here it is dot is there, so it is dot u. So it is dot u. So if you want to find directional derivative of f at x naught y naught, if f is a differentiable function, you can directly use this formula del f at x naught y naught dot u. Otherwise, we have to use the definition of directional derivative. Okay. Then the sufficient condition also I just mentioned. What is the sufficient condition? Suppose f is a function from D subset of R2 to R BMF such that the both fx and fy exist on the some neighborhood. So I just mentioned that thing. So D is the domain and x naught y naught is the point in there. I look at some ball centered at x naught y naught of radius delta. Then in this intersection region, that is the region I marked, there suppose fx and fy exist on that region, and if one of them is continuous, so either fx or fy, one of them is continuous at the point x naught y naught. So in the entire region the function fx and fy exist, and one of them is continuous at x naught y naught, then f is differentiable at x naught y naught. So in order to extend the differentiability at x naught y naught, we need to check whether the partial derivative exists, first of all, in some region, some small neighborhood, whether it exists, is one of them is continuous in that neighborhood. If it is possible, then we can say f is differentiable at x naught y naught. Okay. Now I will go for before going for the problems, I just mention one more thing, mean value theorem for functions of several variables. After that, I will go for the problem. So first I'll just recall what is the mean value theorem we have studied for single variable. Then I will go for the second variable. So let f from some closed interval a b to r, and we assume f is continuous on AB and differentiable on open interval AB. So what is the mean value theorem says? Then there exists C belongs to open AB such that f dash of C is equal to f of B minus f of A by B minus A. So this is the mean value theorem for single variable case. So we have a function from closed interval AB to R, and we are assuming that f is continuous on closed interval AB and differentiable on open interval AB. Then we can find there is a C in open interval AB such that this condition hold. F dash of C is equal to f of B minus f of A by B minus A. So the same things I can extend for two variable case. So this is the two variable case. So U subset of R2 I am taking as an open subset, and f from U to R be a differentiable map. And so I will look at U, this is the U, and I am taking 2 point A and B in there, and I am assuming that the segment joining from A to B, that is the line segment from A to B, is completely contained in U. I am assuming that this line segment from A to B is inside U. Okay. So the segment that is denoted by this notation, this is not means the closed interval AB. This notation says the segment joining from A to B. Okay. Line segment joining from A to B. So we have f from U to R, that is a differentiable function, and we are assuming the segment from A to B is contained in U. That also we assume. Then there exists a C lies between inside the segment. So in between this line we can find somewhere some C. Somewhere we can find some C such that f of B minus f of A is equal to, this is the notation for derivative of f at C, df of C into B minus A, the same one. So, but I cannot write by this notation. Here I am writing f of b minus f of a by b minus a. But here b minus a is a scalar, so I can divide it. There is no problem. But what I will get here, a and b are coming from R2. So b minus a is nothing but a vector. That is why I have written in this way. So this we can write this way, right? F dash of c into b minus a is equal to f of b minus f of a. So here I cannot divide it by b minus a. This is because b minus a is a vector. So that doesn't make sense. So that is why this notation. Here f of a is also, f of b is also a scalar, and f of a is also a real number. So f of a minus f of b I can take. And this will give a matrix or a vector. df of a is a vector, and b minus a is again a vector. This multiplication stands here is the dot product. So you have to multiply that point wise, component wise. So this is nothing but the dot product, not just a simple multiplication, because this df of c is a vector. This is my alpha beta, and this is another vector. So their multiplication is nothing but a dot product. Okay, so that will give a scalar. So left hand side we have a scalar, right hand side also we have a scalar. So this make a sense. Okay, this is the mean value theorem. So only thing we need to look at if you take 2 point A and B, you have to look at the segment joining A and B. Then we will look at f of b minus f of a by then the statement is that in between the segment there is a point C such that f of b minus f of a is equal to df of c into b minus a. Yeah. Any doubt? Any question? Hello?
No, you can continue.
Okay, okay. So this is the mean value theorem for functions of several variables. Now I will go for one example of differentiable functions. Then I will move on the problems from JAM. So we will look at some examples of differentiable functions. So I just want answer from people. I just want to know whether you have understood these things. Because f of x, y I have defined as square root of x square plus y square for all x comma y belongings to R2. Question is this: is f is differentiable at 0, 0. So can someone tell this, if this, because we have already seen these examples and we have mentioned some property of this example. Is this f is differentiable at 0, 0? I will give 1 second to people to answer. If somebody want, they can tell. No one want to answer. Okay, so what we have understood from the definition of differentiability? Suppose f is differentiable, then there exists some alpha beta. That alpha is nothing but fx at x naught y naught, and beta is nothing but fy at x naught y naught. So what is the definition? If f is differentiable, sorry, suppose f is differentiable. Suppose f is differentiable at 0, 0. There exists some alpha beta in R2 such that this thing happen, right? Limit hk tending to 0, 0, f of 0 plus h, 0 plus k, minus f of 0, 0, alpha times h minus beta times k by this happen to be 0. So that is the meaning of differentiability at 0, 0. So if f is differentiable at 0, 0, then there exists some alpha beta in R2 satisfying this condition. What is that alpha? Alpha is nothing but partial derivative at fx at 0, 0, and beta is nothing but fi at 0, 0. So now you look at the function. What is the function? F of xy is equal to square root of x square plus y square. So the question is whether the partial derivative at 0, 0 exists or not. This one I have done in the last class itself. So if you want, I can do it again. So you look at fx at 0, 0. By definition, what is this? Limit h tends to 0, f of 0 plus h 0 minus f of 0, 0 by h. What is this? Limit h tending to 0, square root of h square. So this f of 0, 0 is 0. So this square root of h square by h. So this is nothing but limit h tending to 0 mod h by h. This does not exist, right? Does not exist. So similarly, you can look at fy at 0, 0. That also does not exist. Fy at 0, 0 also does not exist. Okay. The similar way you can look at. Only difference is instead of 0 plus h, it will come 0 comma 0 plus h. Okay. So what you have understood from here, fx at 0, 0 and fy at 0, 0 both are does not exist. Then you can say this function is not differentiable at 0, 0. Suppose it is differentiable at 0, 0, both the partial derivative should exist. Fx at 0, 0 and fy at 0, 0 must exist. That is our alpha and beta. But both of them does not exist. So this function is not differentiable at 0, 0. It's not differentiable. Not differentiable at the point 0, 0. Okay. So f is not differentiable at 0, 0. Okay. Now this is the one example. So the only thing we need to worry about this alpha and beta. For finding the derivative, this alpha has to be the fx at 0, 0 and beta has to be and fy at 0, 0. So whatever the question comes, so your alpha has to be the partial derivative at that point with respect to x, and beta has to be the partial derivative with respect to y at that point. Okay. So in this case, the partial derivative does not exist, so the f is not differentiable. Okay. So now we will go for previous questions. So is this visible? This question?
Yes.
Yeah. Okay. Yeah, we will start. Look at this question first. This is 2018 question. You just look at once the question. So you have a function fxy. It is given that xy by x square plus y square power alpha, where xy not equal to 0, 0, and for xy equal to 0, 0, the value is 0. The question is which of the following is true for f at 0, 0. You wanted to look at which of the following things are true for the function f at the point 0, 0. So we will look at each of the options separately. For alpha equal to 1, we will look at first. So for alpha equal to 1, the first option I will look at. So this is the case alpha equal to 1. So what alpha is equal to 1, what is the function? F of xy is equal to f of xy is equal to xy by x square plus y square. Here alpha is 1, xy not equal to 0, 0, and 0 for xy equal to 0, 0. Now tell me whether this function is continuous or not. I have discussed this function many times. So last class also I have discussed. Today also I just tell some property of these functions. So now tell me whether this function is continuous or not. Somebody to tell. So first of all, whether the limit at 0, 0 exists? Is there any comment? Whether the limit at 0, 0 exists? My question is whether this exists.
No, sir, the limit would not exist.
Yeah, limit at 0, 0 f of xy does not exist, right? This does not exist. Why?
Because when we take the curve y is equals to mx, the value of limit depends on m.
Yeah, yes, correct. So if I look at the curve y equal to mx, so I have to consider curves passing through the point 0, 0. So I will look at a family of curve passing through this 0, 0. So that is generally denoted by y equal to mx. Okay. M is sum. M belongs to sum. So whenever m vary, we will get a different curve. Okay. Now you look at along this curve, you find the limit. So y equal to mx, you have to substitute y equal to mx in this equation. What you will get in? So f of x comma mx is what? F of x comma mx is nothing but yeah, m x is m x square divided by x square plus m square x square. So that will be giving m by 1 plus m square in m square. So both x square you can take from the denominator, that will cancel. So the final value is m by 1 plus m square. So while then limit xy tending to 0, 0 along y equal to mx will give you nothing but m by 1 plus m square. So this value will be different for different m's. Suppose I am taking y equal to x. That is the case m is equal to 1. In that cases, you will get 1 by 2. If I am taking m equal to 2, in that cases, I will get 2 by 5. So you will get a different value for different curves. That means the limit at 0, 0 does not exist. So this limit itself does not exist. Then what about the first option? First option says f is continuous but not differentiable. So but this limit does not exist. So first option is wrong because continuity is not guaranteed because the limit itself does not exist. So the function is not continuous at that point. So the first option is wrong. Now you will look at the case alpha equal to half. So you look at the case for alpha equal to half. The second one, this is the option B. In this case, alpha is half. So what about your f of xy? This is xy by square root of x square plus y square if xy not equal to 0, 0 and 0 if xy equal to 0, 0. Okay. So now you look at again the limit value. So I will give you one observation that you have to make. So the thing is, suppose you look at this function here in the numerator you have a xy and in the denominator you have square root of x square plus y square. So in the numerator you have a polynomial in x and y. is degree is at least 2. That is 2. Degree is 2. And in the denominator, you have a polynomial in which the degree is less than 2 because there is a square root. Okay. Inside that square root, you have a polynomial. So like that, you can observe whether this exists or not. So only thing you need to worry about, if both have the same degree, numerator one polynomial and denominator is another polynomial, and if both have the same degree, we cannot conclude anything. And suppose something in the numerator is more degree than the denominator, you can conclude that, you cannot conclude, but you can have an observation that this will be continuous. And the other thing is, suppose the denominator having the highest degree, then also you can have the observation that it does not have limit exist. So for these cases, I have a observation that the limit will exist at 0, 0, but I can do it more precisely by using the polar coordinate. But before going for that polar coordinate thing, you should have some intuition whether this exists or not. That how do you get that thing? By looking the function, you can understand whether if I apply the polar coordinate system, whether it will work or not. Okay, for this one, I will say the limit will be exist. So just wanted to compute the limit. What I will do is, I will look at the polar coordinates. So you take x equal to r cos theta and y is r sin theta. Then I will look at the function f of r comma theta. What is that? In the numerator, I have r square cos theta sin theta, and in the denominator I have r. Okay, so this will be nothing but r times cos theta sin theta. Now if I look at limit xy tending to 0, 0, or you can say if you look at modulus of f of r comma theta, this is always less than or equal to r. Okay, now we wanted to find this limit xy tending to 0, 0 f of xy. This is same as limit r tending to 0 f of r comma theta. So what you will get, while limit r tending to 0, this left side you will get 0. So the right side you will get 0. Then left side also has to be 0 because this is the modulus value, right? So this will implies limit r tending to 0 f of r theta is 0, right? As r tending to 0, from this equation, from this one, you can say right side is getting 0. So this side also has to goes to 0 because this is always greater than 0, right? Yeah. So we will get limit r tending to 0 of f of r theta is 0. Okay. So what about the limit? So that is limit xy tending to 0, 0 f of xy is nothing but 0. That is our f of 0, 0. Okay, this is the case. Now I just wanted to look at the second option. What is the question? So if alpha equal to half, whether f is continuous. Okay, so we got f is continuous, right? Limit xy tending to 0, 0 f of xy, we got f of 0, 0. Only we need to worry about the point that 0, 0. So for alpha equal to half, f is continuous at 0, 0. Now I wanted to look at whether f is differentiable at 0, 0. Okay, so suppose f is differentiable, first thing we have to look at alpha and beta. What is our alpha? Alpha is the partial derivative with respect to x at 0, 0, and beta is the partial derivative with respect to y at 0, 0. So you just observe first whether the partial derivative at 0, 0 exists or not. So you look at fx at 0, 0. What is that? That is limit h tending to 0 f of 0 plus h minus 0 by f of 0, 0 by h. Okay, so what will be this value? So you look at the function. What is your function? Alpha equal to half case, this is your function. Then what about the first one? F of 0 plus h is h only. So f of h comma 0. So the numerator you will get 0, right? Because xy term is coming there. So you will get h into 0 in the numerator. So totally you will get 0 here. So the numerator is completely 0, right? So you will get numerator is fully 0. Denominator is h. Then limit change to 0. This is in fact 0 only. So fx at 0, 0, you will get 0. Now similarly you look at fy at 0, 0. What is that? Limit h tending to 0. F of 0 comma h minus f of 0, 0 by h. That is again you will get 0, right? Because here you have x into y is coming, x is 0 there. So both the partial derivative are existing and they are 0. So from this information we cannot conclude anything. If f is differentiable at some point, I know the partial derivative will exist. But existence of the partial derivative does not guarantee the differentiability of the function. The only thing we need to worry about whether the partial derivative are continuous in some neighborhood. In that way you can look at, or we can look at does there exist some alpha satisfying the property, alpha and beta satisfying the property. Suppose there is an alpha beta exist, that alpha has to be your fx at 0, 0, right? Suppose, so you're right. Suppose f is differentiable. F is differentiable. Then there exists alpha beta in R2 such that, suppose it is differentiable such that limit hk tending to 0, 0 f of hk minus f of 0, 0 minus alpha h minus beta k divided by square root of h square plus k square. This has to be 0. Suppose f is differentiable, there exists some alpha beta such that this has to be 0. Okay. Then what? Then that alpha beta exists. What has to be that alpha beta? If f is differentiable, that alpha beta has to be fx at fx at 0, 0, and beta has to be fy at 0, 0.
f by h 0, 0.
Yeah. So you just substitute those values here. Then if f is differentiable, your alpha should be then alpha should be equal to this one, fx at 0, 0, and beta should be is equal to fy at 0, 0. Correct. Now suppose I substitute these values here. What happens? I got already fx at 0, 0. What is that fx at 0, 0? 0. Fy at 0, 0, that is also 0.
0.
So if I substitute here, what I will get? I can write limit hk tending to 0, 0 f of hk. What is f of 0, 0? That is also 0, right? F of 0, 0 is also 0. So f of hk divided by square root of h square plus k square. Because alpha is 0, beta is 0, and f of 0, 0 is also 0. I should get this has to be 0. Then only I can say the partial derivative exists, right? Differentiability I can guarantee. I should get this limit value should be 0. If it is not 0, I cannot conclude I can say that if it is not differentiable at 0, 0. So you should find this limit first. What is this limit? You look at your function f of xy is xy by square root of x square plus y square. So if I substitute this thing here, what you will get? So this is equal to limit hk tending to 0, 0. F of hk is hk divided by square root of h square plus k square. And whole divided by square root of h square plus k square is there. So if I multiply these things, what I will get? This is nothing but limit hk tending to 0, 0, hk divided by h square plus k square. Okay. So whether this exists or not?
Do not exist, sir.
Yeah, do not exist. So what actually I got, limit hk tending to 0, 0, f of hk by square root of h square plus k square does not exist. So what it concludes? It concludes f is not a differentiable at 0, 0, right? So I can explain once more this. Suppose f is differentiable, then there exists alpha and beta in R2 such that this relation holds. Such that this relation holds. So there must exist some alpha beta satisfying this relation. Then only we say f is differentiable at 0, 0. Okay. So suppose f is differentiable, then there exists alpha beta in R2 such that this condition holds. Okay. Then that alpha has to be fx at 0, 0 and beta has to be fy at 0, 0. Okay. Suppose such a alpha beta existing, that alpha has to be fx at 0, 0 and beta has to be fy at 0, 0. So I just substitute the values of fx at 0, 0 and fy at 0, 0 in this equation. So what is your fx at 0, 0? That is 0. What is your fy at 0, 0? That is 0. And this f of 0, 0 is also 0. So all those values I substitute here. So the remaining thing is f of hk divided by square root of h square plus k square. So in order to say the f is differentiable at 0, 0, we only need to look at limit hk tending to 0, 0, f of hk by square root of h square plus k square. Suppose this limit is equal to 0, we can conclude that the function is differentiable at 0, 0 and the derivative is 0, 0. But so that I just find this limit, whether this exists or not. I just computed that. So I just substitute the value of functions and I computed and I understood that that limit does not exist. So the limit hk tending to 0, 0, f of hk by square root of h square plus k square does not exist. So that means f is not differentiable at 0, 0. So if it is differentiable at 0, 0, the derivative has to be 0, 0 only. Because partial derivative at 0, 0 is 0 and partial derivative at 0 with respect to y also 0, 0 is also 0. So I have to plug that values here in as alpha and beta and I have to compute this limit and it should be exist and it has to be 0. Then only I can say that is the derivative exists at 0, 0. But here I got that limit is not existing. So it says f is not a differentiable at 0, 0. So for alpha equal to half case, function is continuous, but it is not a differentiable at 0, 0. Now we will go for the case alpha equal to 1 by 4. Okay. So for alpha equal to 1 by 4, you look at the same way. So alpha equal to 1 by 4. What is your function? F of xy is equal to xy divided by x square plus y square whole raised to 1 by 4. If xy not equal to 0, 0 and 0, if xy equal to 0, 0. Okay. If alpha equal to 1 by 4, f of xy is this. Okay. Now again you will again you look at this function. The denominator have more degree than the numerator have more degree than the denominator. So I have the intuition that the limit will exist. So again I just prove using the polar coordinate system. So I take x is equal to r cos theta, x equal to r cos theta, y equal to r sin theta. So what your f of r theta? Tell me. F of r theta is equal to r square cos theta sin theta divided by r square raised to 1 by 4, right? X square plus y square is r square. So this is r square cos theta sin theta divided by square root of r. So you can just bring this here, then it will be nothing but r 2 minus half I will get. So it is 3 by 2, right? 3 by 2 cos theta sin theta. Okay. Now again, as r tending to 0, what happens? As r tending to 0, this value goes to 0, right? Limit r tending to 0, f of r theta, that is 0. So this implies limit xy tending to 0, 0, f of xy is equal to f of 0, 0. So the function is continuous at 0, 0. So that is the third option. If alpha equal to 1 by 4, f is continuous. Okay. Now I wanted to look at the differentiability, whether the function is differentiable at 0, 0. So first you, again as in the case, you look at partial derivative with respect to x. What do you get fx at 0, 0? Fx at 0, 0 is limit h tending to 0, f of h comma 0 by f of 0, 0 by h. What is that? That is 0, correct? As in the same case, you substitute here x is h and y is 0, right? So in the numerator will turn out to be 0. So fx at 0, 0 is 0. Similarly, fy at 0, 0 is also 0. Fy at 0, 0 is again limit h tending to 0, f of 0 h minus f of 0, 0 by h. That is again getting 0. Okay. Now, okay. Now you look at, again I wanted to look at whether f is differentiable. So what I wanted to look at, this is the definition for differentiability, right? Limit hk tending to 0, 0, f of hk minus f of 0, 0 minus alpha h minus beta k divided by square root of h square plus k square has to be 0. If it is 0 for some alpha beta, then we say f is differentiable at 0, 0. So if such alpha beta existing, that alpha has to be the partial derivative at 0, 0, and if beta has to be the partial derivative with respect to y at 0, 0. And I got, in this case also, the partial derivative at 0, 0 is 0. Partial derivative with respect to y at 0, 0 is also 0. So I can put this alpha as 0 and beta as 0. And f of 0, 0 is 0 only. So the only thing I need to verify this thing, right? Whether this value is exist or not. So only thing I need to verify what this. I need to verify limit hk tending to 0, 0, f of hk divided by square root of h square plus k square, whether this 0 or not. I just wanted to verify this. Okay, if it is 0, I can say the function is differentiable and the derivative is 0, 0. Because the alpha here is fx at 0, 0, that is 0. Beta here is fy at 0, 0, that is also 0. That we have already seen. So only thing I need to verify whether this exists and this value is 0 or not. So you just compute this value. So what will be the value? What is f of hk? F of hk is equal to
K divided by.
this equation. I have to substitute hk by, yeah, it is hk. In hk will be in the numerator. Denominator I have h square plus k square whole raised to 1 by 4, right? Yeah. Then again I will look at f of hk divided by square root of h square plus k square. So that will be hk divided by square root of h square, sorry, not square root. This I can write in the h square plus k square whole raised to 3 by 4, right? 1 by 2 plus 1 by 4. So it is, yeah, 3 by 4. Okay. Now tell me whether this limit exists or not.
Exists, sir.
Yeah, limit hk tending to 0, 0, f of hk by square root of h square plus k square. What should be that thing? Yeah,
0.
limit, yeah, hk tending to 0, 0, hk by square root of plus k square whole raised to 3 by 4. This has to be 0, right? So why? Again, if you want to do more precisely, you can do by using the polar coordinate. Again, you have to substitute h equal to r cos theta, k equal to r sin theta. Then in the numerator, you will get something r square cos theta sin theta. In the denominator, what you will get? So if I substitute in the polar coordinate way, what you will get in the numerator? I can write it here. Numerator, I will get r square cos theta sin theta in the numerator. So if I look at the polar coordinate, and in the denominator, what I will get? I will
R
get
raised to 3 by 2.
r raised to 3 by 2. So r square minus, so in the totally, if I can return it, it will be like r raised to 1 by 2 cos theta sin theta, right? Still again, r term is here. So r tending to 0, you will get a 0 only. Again, you can you use the modulus, cos and sin is bounded by 1. Then you tend r to 0. So you will get 0 only. So because of that only you got 0 here. The only thing you need to observe whether the degree, you look at the polynomial in the numerator. So that is a polynomial in hk, its degree is 2. In the denominator, you are having the smaller degree. So it has to exist and it has to be 0. Okay, that is one observation only. If you want to do it more precisely, you have to convert it by polar coordinate. Okay, so this
Sir, I
limit
have a doubt.
exists. Yeah, you tell me.
Sir, you are applying the polar coordinates here. So, can we
Hmm.
apply the polar coordinate system even if we know that the limit does not exist? Or only in the case we know the limit exists, then only we can apply the polar coordinate system?
No, you can apply polar coordinate in general also, but that does not give you any conclusion. Like suppose you have these cases where we have seen the limit does not exist for this one, hk by square root of h square plus k square, right?
Yes, sir.
So if you substitute polar coordinate here, what you will get? Tell me. The numerator, what you will get?
Numerator is r square sine theta cos theta.
Yeah, in the numerator you will get r square
Sine theta cos
sin theta cos theta, and in the denominator you have r square, right? So this r square will getting cancelled. Okay.
mm, mm,
So what you will have the remaining thing, f of r theta.
sine theta cos theta.
Yeah, then you cannot conclude anything.
Yes.
As r tending to 0, you cannot conclude, right? It's depend upon theta. Suppose theta you give 0, or suppose theta you give pi by 4. What you will get value? Theta equal to pi by 4 is the line y equal to x.
Yes, sir.
So if you give theta equal to pi by 4, what value you will get? Sin pi by,
Theta is pi by 4, 1 by 4.
yeah, theta
Half.
equal to pi by 4 case, half you will get. So if you take theta is equal to some other value, 3 pi by 4, what you will get? Again, you will get a different value. So it is same as to consider the line y equal to x or y equal to 2x. Suppose you consider the line y equal to x. In that cases, theta is pi by 4. If you take the line y equal to 2x, in that case you can find the appropriate theta. So in that value you will get, one is you will get 1 by 2, other you will get 2 by 5. So do you remember while approaching y equal to x, we got 1 by 2. While approaching
Yes.
y equal to 2x, we got 1 by 2 by 5. While approaching y equal to 2x, we got 2 by 5. While approaching y equal to x, you got 1 by 2. So that is the two different value we got there. So if you look at that way, then you have to look at the corresponding theta. So different theta, you will get different value. So it's
So
depends
in
upon,
general, is it true that if the limit does not exist, then the polar coordinate also do not give any result?
yeah, if even if the limit does not exist also, By converting polar coordinate, you can tell that it does not exist. By this way, you can say. So for this example, what I did, f of r theta, I got as sine theta cos theta. Now I have to say this limit is depending upon theta. If you vary different theta, you will get different value. That cannot be equal. For all theta, it has to be equal. Then only you can say the limit exists at 0, 0. You understand? Do you understand that? For different theta, you will get different value. Here the function is depending upon theta there. F of r theta is sine theta cos theta. That is depending on theta. But in the previous, the other cases, you have a r term. Everywhere you have getting an r term. Here also you have r raised to 1 by 2. And the previous one you have r raised to 3 by 2. Everywhere there is a term in r. Whatever theta, if you tend xy to 0, r will goes to 0. Right? Whatever theta you choose, if you tend xy to 0, r will goes to 0. So you will get a 0 only there. Do you understand the difference? So in this case, limit is not depending on theta. Whatever theta you choose, as r tending to 0, f of r theta will goes to 0 there. Because there is a term in r in the expression. But in this case, you have only sine theta and cos theta. There is no term r in the expression. So while you tending to r to 0, it depends upon the theta, which path you have chosen. Suppose you take y equal to x. Along the y equal to x, you are approaching 0. Then theta has to be pi by 4 there.
Pi by 4, yes.
Yeah, if you approach along y equal to 2x, theta has to be something else. So for each cases, you will get different value. So in the previous example, there is an r term. Whatever theta you choose, as xy tending to 0, 0, r will goes to 0. So totally you will get a 0. That is not depending on theta, but here it depends on theta. So you can convert this equation into polar coordinate. Then you can tell that the limit at 0, 0 does not exist. By picking different path, you are getting different value. Do you understand that?
Yes, sir. Yes.
Yeah.
Mahesh,
Yeah.
someone is asking a doubt in the chat box. Instead of solving for particular values of alpha, can we do it in for a general alpha and conclude? I think that is the question.
General alpha is you cannot conclude.
Can I say something here, sir?
Yeah, you can tell me.
Yeah. We can. I think we can generalize this thing. Here, like for alpha equal half, we saw that when we took alpha equals to half, then what do you call?
Yeah, tell me. For alpha equal to half.
Sorry. For alpha, So for just a second.
Yeah, you can. Only difference if you are doing indirectly. If you are doing directly without looking particular cases, what is the difference you will get? So you only wanted to look at for continuity. If you wanted to look at in the expression, you have alpha minus some term will come. So you can conclude using that thing, right? So what kind of alphas it will be continuous? What kind of alpha it will be discontinuous? So directly also you can try that. There is no problem, I think. So, but for understanding it will be better, I think.
Someone has commented something in the chat box.
Yeah.
Can you see it?
What is that? It is there?
Yeah.
I am not able to see the chat box. Okay, 1 minute.
Okay. Whenever 3 minus 2 alpha greater than 0, then we will have it. It is his answer. I just reading it.
3 by 3 minus 2 alpha greater than 0 for differentiability. Yeah. Yeah, yeah, that you can generally do. There is no problem. Yeah, that you can directly you can compute and you can do that. I think there is no problem. So for alpha greater than 3 by 2, it is happen to be the differentiability.
Okay.
Yeah. So I
Okay.
have not done in that way. I have look at each options separately. So that is possible. The what they have said is possible. You don't worry about alpha. You directly compute it. Then you can conclude something for alpha so that it is differentiable. So somebody had given answer that for alpha greater than 3 by 2, it is differentiable. That's fine. So I have look
Okay.
at each in a separate way. That's all.
Okay, no problem.
Yeah. Yeah. Now let us go for another question. 1 minute. Before going for that, I just wanted to move this. Okay. So let us look at this question. Can you see this? Is it visible? Okay. Fine. I think this is very simple. You guys can tell. Is it okay?
Yes.
Yeah.
Yes, yes.
Somebody can easily find out, or I can try this. You only wanted to look at fx at 0, 0 and fy at 0, 0, right? So what is fx at 0, 0? This is limit h tending to 0, f of 0 plus h, f of 0, 0 by h. So that will be, what is that? Or 0, yeah. What is 0 plus h? So you have h cube in the numerator, right? So it is limit h tending to 0, h cube divided by h square plus y is 0. So this is h square only. There is no term extra. And whole divided by h. So what you will get? This is nothing but limit, yeah, h0, h
Some
cube
of
by
them
h.
are commenting that option B is right.
Yeah, it's 1. Correct. Option B is correct. Yes. I just do it. Fy at 0, 0 is limit h tends to 0, f of 0h minus f of 0, 0 by h. This is in fact 0, right? Because x is 0. If you put x equal to 0 in the numerator, x cube is there. So total term is turned to be zeros. So whenever x is 0, you will get numerator is 0. So only thing you need to worry about f of h comma 0. So in that cases, you will get h cube by h square there. And whole divided by 1 h is there. So you will get a 1. So option B is correct. Yes, this one is the correct answer. So you got this. Fx at 0, 0 is 1 and fy at 0, 0 is 0. I think it is okay, right? Yeah. I will go to another question. So you can, somebody can try this also. This is also similar kind of questions. Somebody can quickly tell this. I just don't want to do all kind of similar questions.
Students, you can post your answer in chat box or you can directly unmute your mic and say. Okay.
This is as simple as that. You have already seen some example. Only you use the definition of partial derivative 0, 0 and partial derivative yeah, with respect to x and y at 0, 0. So each you compute and tell.
Sir, 0.
0, 0 is not correct, I think. Not 0 is correct. I think it is 1. Okay, I can do if you want. I just don't want to spend time. So fx at 0, 0 is there. What is that? Limit h tending to 0. F of h0 minus f of 0, 0 divided by h. So what is f of h0? So here x is h. So if you substitute here, what you will get? This will be h by, yeah. So limit h tending to 0, h by h into square root of h square whole divided by h. What is this value? Tell me. Somebody tell me this value. What is square root of h square?
Mod H.
Mod h. So both mod h will cancel, right? So this
Yes,
is
sir.
nothing. Yeah. So this is nothing but a 1.
1.
Yeah. Then what about the other one? Fx at fy at 0, 0. This is limit h tending to 0, f of 0h minus f of 0, 0 by h. What is f of 0h? In that case, x is 0. If x is 0,
0.
your function is 0, right? So it's totally 0, right? This thing is nothing but 0. So what's your answer? Which one is correct? I think option C is
1.
correct. Yeah. Do you understand this? There is nothing. You just use the definition of partial derivative. That's all. Okay. Yeah, I will look at another question. I think it is okay, right? Is there any comment or anything?
Yes. Continue.
Yeah. Yeah. Okay. Now you look at another question. These all are same kind of questions only. You can easily do this. Okay. For this question, you wanted to look at the continuity. So you just look at the domain where it is defined, y equal to 0 and y not equal to 0 case. So only you need to worry about the point in which y equal to 0, right? So only you need to worry about the points like this, a comma zeros. So these points you wanted to look at whether this function is continuous or not. So you have the domain like this, and y equal to 0 is the x-axis. So this is the line y equal to 0. Okay. So you don't know anything about in that line, but outside of this line, your function is defined, right? Well defined, like x minus y cube. Okay, that this is the function. Outside, this is the function, and on the line, your function is this. So outside, everywhere, the function is continuous. Okay, and only we wanted to look at the point 0, 0. Okay, fine. At the point 0, 0. Sorry, you only wanted to look at the continuity at the point 0, 0. Okay. Sorry, no, we don't want to worry about the general point. Okay, we wanted to look at the point 0, 0. Okay, fine. So what you wanted to look at? You want to look at limit xy tending to 0, 0 f of xy. What is that? So what will be that? This will be equal to okay. So yeah, 1 minute. So you just consider your function is this one, right? X minus y cube into sine 1 by x. Okay. So that is okay. So this is limit xy tending to 0, 0 x minus y cube sine 1 by y. Okay. So I can split the limit into for two functions. So what about the first one? Limit xy tending to 0, 0, x minus limit xy tending to 0, 0, y cube sine 1 by y. Okay, what about the first one? Tell me what is the limit? Limit xy tending to 0, 0, x is
0.
0. Okay, this is 0. Yeah, what about the second one? So second one is a function of single variable only, right? Yeah, is somebody want to add something? Yeah, tell me. What about the second one? Limit of the second one?
Limit will be 0, sir.
Yeah, that also 0 because
Yeah, because sine is a bounded function.
Yeah, yes, correct.
And the other y cube goes to 0 when y tends to 0. So this whole thing will goes to 0.
Yeah,
Because
this
sine is a
totally you will
bounded
get a 0. Correct, correct, correct. So you can think this as a function of single variable, right? And you can bounded the sine value. Sine is bounded by 1. As y tending to 0, this happen to be 0. So this second one is also 0 and first one is also 0. You got limit xy at 0, 0, f of xy is 0. That is nothing but your f of 0, 0. This is nothing but f of 0, 0. So the function is f is not continuous is wrong option. So f is continuous. Now you wanted to look at partial derivative. Okay. So first, second option you wanted to look at about whether this is differentiable or not. So you wanted to look at the function is differentiable at the point 0, 0. So first thing you wanted to worry about the partial derivative, right? Whether this fx at 0, 0. What is fx at 0, 0? Limit h tending to 0, f of h0 minus f of 0, 0 by h. What is that? That is equal to, yeah, what is f of h0? So that is the case y equal to 0, right? So this first one is the case y equal to 0. So your function is x. Okay. So this will be nothing but limit h tending to 0, h by h. So you get 1. fx at 0, 0, you got 1. So what about in general, if you look at fx at any point I am looking. So why I wanted to look at any point? Okay, I will come to that point. Just before that, I will look at whether the partial derivative at y exists. So you look at fy at 0, 0. What is that? That is again limit h tending to 0, f of 0h minus f of 0, 0 by h. Okay, this is limit h tending to 0. What is the function f of 0h? 0h is the second case, y not equal to 0. So your function is minus h cube into sine 1 by h by h. So again, this is equal to limit h tending to 0 minus h square sine 1 by h. So this value again goes to 0, right? Okay. So fx at 0, 0 you got, that is 1. Fy at 0, 0 is 0. So both the partial derivative at 0, 0 exist. Fine? Is that fine? Hello? Is that fine?
Yes, sir.
Okay. So the partial derivative at 0, 0 is 1 and partial derivative at 0, 0 with respect to y is 0. Now, this is not enough to tell whether the function is differentiable or not differentiable. So only thing we need to look at partial derivative should be exist in some small neighborhood and whether it happen to be continuous or not. That is the important thing we wanted to verify. Then only we can conclude that the function is differentiable or not differentiable. Okay. So in order to conclude the differentiability, I just look at the partial derivative in a small neighborhood, or in generally I will look at. So I will look at fx at some arbitrary point AB. Or you can directly look at the differentiability using the definition. I am using this method. That's all. Fx at a b I will look at for general point a comma b. I don't worry about whether a is any. Okay, I will do it as a two cases, b equal to 0 and b not equal to 0. So what is this value? This is equal to limit h tending to 0 f of a plus h b minus f of ab divided by h. So you can just compute it. This will be equal to limit h tending to 0. What is f of a plus h comma b? Just using, so I will use the cases b not equal to 0. So I may mention here b not equal to 0. I have to look at it as in the two cases b not equal to 0. So b not equal to 0, what is your value? Your function value is the second one. So in that cases f of a plus h comma b is, this is a plus h minus b cube sine 1 by b minus a plus b cube sine 1 by b divided by h. Okay, so this b cube sine 1 by b, b cube by sine 1 by b, that will cancel. Then that a also will cancel. Then the remaining is this is equal to limit h tending to 0 h by h. That is nothing but a 1. So for the case b not equal to 0. Now b equal to 0, what you will get? For b equal to 0, you take b as 0. Then again this will be equal to, so in that cases your function value is the first one, right? B equal to 0 means the first value, first case. So that will be limit h tending to 0 f of a plus h comma b will be a plus h minus a divided by h. Again you will get 1. Do you understand this? For b equal to 0 you will get so I am looking fx at a comma b. B equal to 0 case I got 1. B not equal to 0 case also I got 1. So it means fx at a comma b is 1 for every a comma b, right? Fx at a comma b is 1 for all a comma b in the domain in R2. So whatever a comma b you take, you got fx as 1. So that means fx is identically a continuous function, right? Fx is identically equal to 1. It's a continuous function. Now again you wanted to go for fy, partial derivative with respect to y. So what you want to look at, you wanted to say whether the function is differentiable or not. In order to prove whether it is differentiable, you only need to look at you consider the small neighborhood of 0, 0. Inside that small neighborhood, you wanted to prove that partial derivatives are existing and one of them is continuous there. If one of them is continuous and both the partial derivative are existing in the small neighborhood, then we can say f is differentiable at 0, 0. That is the sufficient condition for differentiability. So I am going to use that. So I got partial derivative with respect to x is identically 1. So that partial derivative is existing everywhere in the domain. Not only that, that is a constant function, so it is a continuous function. So now I only wanted to worry about the partial derivative with respect to y, whether the partial derivative with respect to y exists or not. If it exists, I can conclude that f is differentiable. Okay. So I will look at partial derivative with respect to y. Fy at a comma b. So that is again limit h tending to 0 f of a b plus h minus f of a comma b divided by h. So in this case also I have to look at two cases, b not equal to 0 and b equal to 0. B not equal to 0, what you will get? This will be equal to, so b not equal to 0 means you have to worry about the second case. So again you have this one, your value is limit h tends to 0 a minus b plus h cube sine 1 by b plus h minus a b. We will get plus here b cube sine 1 by b divided by h. So you can see that this a getting cancelled. Then the only thing you need to look at whether this limit exists or not. So you can do it by not going for that. You can look at this. This will be nothing but b cube sine 1 by b. The other one is minus b plus h whole cube into sine 1 by b plus h by h. So this limit you can find. So again, you can look at it as a function, L'Hospital rule. You can take the derivative with respect to h in the numerator. Again, the denominator term will turn out to be 1. It is of the form 0 by 0. This is a single variable case as h tends to 0, right? It's a function of h in the numerator and function of h in the denominator. You can compute the limit. You can say this will exist. So that is directly you can do by L'Hospital rule. I'm not going for that. You can just take the derivative in the denominator. That will turn out to be 1. Numerator term, what will be the derivative? You have to use the product rule for this one. Both the term having h. So this will exist. You can directly compute there. So this thing will exist. This exists. Similarly, you can look at b equal to 0 case also. What you will get, that is limit h tending to 0. So once b equal to 0, this term is turned out to be simply a, and here you have this term I can write as this way. So this is nothing but f of a comma h minus f of a comma 0 divided by h. So this will be equal to limit h tending to 0 a minus h cube sine 1 by h minus a divided by h. Again this h's will cancel, then you will get limit h tending to 0 minus h square sine 1 by h. This is again 0. Okay. So what I got, I have found partial derivative of f with respect to y at the point a comma b in both the cases. So I only wanted to look at whether this exists or not. So this value you can find by L'Hospital rule, just to do the routine computations only. The denominator, if you take derivative 1, you will get 1, and numerator also. I only wanted to worry whether this exists or not, because for the first cases, partial derivative with respect to x, I have find it that it is a constant function 1 throughout the domain. So partial derivative with respect to x will exist in the small neighborhood of 0, 0, and it will be continuous throughout. That is a constant function 1. Now I am observing that whether the partial derivative with respect to y exists or not. So that existence also guaranteed. So I have found that the partial derivative with respect to y exists throughout the domain. So the partial derivative is existing throughout the small neighborhood of 0, 0. Both the partial derivative is existing in the neighborhood of 0, 0, and fx is continuous throughout the domain. So I don't want to worry about more. So that will implies f is differentiable at 0, 0 by the sufficient condition for the differentiability. So only thing I need to worry, either one of them has to be continuous in the small neighborhood, and both has to exist. So both are existing, and the partial derivative with respect to x is continuous. So by the sufficient condition of differentiability, I can tell that f is differentiable at 0, 0. So do you understand this, or you have any doubt? So this is the last option is correct. F is differentiable. Is there any doubt?
Sir,
Yeah.
without showing this, sir, without showing this partial derivative is continuous, how can we prove from directly? How can we prove directly from that formula? The F is different.
So then again, you have to go for the if suppose F is differentiable at 0, 0, then what is your derivative? What has to be your derivative? Alpha beta, right? Alpha beta is nothing but
Yes.
here alpha is that has to be fx at 0, 0. The other one will be fy at 0, 0, right?
F by 0, 0.
So
Yes,
both
sir.
are
Yes, sir.
both I have founded that is 0, right? Fx at 0, 0 is sorry. Fx at 0, 0 I founded 1, and
Is
fy,
1. Is 1.
the other one is 0, right? So
Yes, sir. Yes.
if you plug that thing into your expression, what you have to look at? Limit
HK tends to 0, 0. H
HK
minus K.
yeah 0, 0 f of HK
H
minus f
by
of 0. Yeah, f of 0, 0 is 0 only, minus alpha h. Alpha is 1 here, so minus h divided by square root of
H square plus K square.
K square.
K
That
square.
should exist. Now again, you have to look at the cases k equal to 0 and k not equal to 0.
Okay, sir.
Again, you have to look at the two cases. So for k equal to 0, you have to consider the first function, right?
Okay, okay.
So what is your for k equal to 0? What is your f of hk? That is
F of H.
H
by
is
H by H.
no. For k equal to 0, what is your f of hk?
F of HK is H.
H. So here you will get h. So numerator you will get h minus h.
Yes.
So that will be 0, right?
Yes, sir. Yes.
So numerator you will get h minus h, that will be 0. Then for k not equal to 0, what you will get? Again, you have to go for k not equal to 0 case. Your function value will be what? So for k equal to 0, what you got? Tell me. I can write it here, right? K equal to 0 case, your f of hk is h. So in the numerator, you will get f of hk is nothing but h only. So numerator you will get h minus h. So numerator term will be 0, right? So totally you got 0. So in that case, limit hk tending to 0, 0, f of hk. So the total term has to be 0, right?
Yes, sir.
That is equal to 0. Okay. So I don't have space to write. Okay, that will be 0, right? Okay. Then for k not equal to 0 case, I will write somewhere here. Okay. Okay, for k not equal to 0 case, you have to look at this value. So the numerator, what will be? It will be h minus k cube sine 1 by k minus h will come divided by square root of h square plus k square. So this h will cancel. Again, you have to find the limit. You have to find the limit hk tending to 0, 0, k cube sine 1 by k divided by square root of h square plus k square. That you have to find. That should again you can use the here k square k cube you can write as k square into k, right? So k square by square root of h square plus k square will be less than or equal to 1. Is that okay?
Sir, once more.
Yeah, I will write here. So the numerator you have this, right? I will write it as this way: k square into k into sine 1 by k divided by square root of k square plus h square. So if you look at k square and square root of k square plus h square, Not like that. Yeah, not k square. I have to take k. Sorry, not k square. I have to take k. This is not k square. I am taking k here, right? So I will look at the modulus value throughout. So here I will look at modulus k. This will be less than or equal to this, right? Modulus of k will be less than or equal to square root of k square plus h square. Is that correct or not?
Yes, sir. Yes, sir.
So once you square on both sides, you will get, this will be bigger, right? Okay. So I can write this total value will be less than or equal to k square. Am I right or not? Because sine 1 by k is bounded by 1 and k by root k square plus h square is bounded by 1. Then the only thing remaining is k square. Is that correct or not?
Yes, sir.
Yes. Now as hk tending to 0, 0, what happens to this value? K square will goes to 0, right? Hello?
Yes, sir. Correct.
So the right hand will go to 0. So the left hand also has to go to 0. So limit hk tending to 0, 0, k cube into sine 1 by k divided by square root of h square plus k square. That total term is going to 0. Is that okay?
Yes, sir. Clear.
Yes.
Sir, can we use polar coordinates directly for this question?
Polar coordinate, that also possible. I have not tried that thing. You just try that thing.
Okay. Okay, sir. Thank you, sir.
Okay. So I think this is okay, fine.
Yes, sir.
Okay. Okay, we will look at another question. So what I have done here is for these questions, two different way you can try. One way I have find out partial derivative all point and I look at the partial existence of the partial derivative in the small neighborhood of 0, 0. I have conclude one of them is continuous. That is partial derivative with respect to x. I am getting that is identity function 1. So I will get it is a continuous function. So I can conclude from that that f is differentiable. Or you can directly use the definition of derivative and you can find the derivative there. Okay, at 0, 0. So f is a differentiable function at 0, 0. That is the correct answer. So now you can look at another question. So this is the function you have. So f is from R2 to R and f of xy is given by this. So here you wanted to find the partial derivative, second order partial derivative of f at xy at 0, 0, and similarly for the order we have changed. First you have to take the derivative with respect to y, then with respect to x. The other one is derivative with respect to x you have to take first, then derivative with respect to y. So first I will look at fx at so to find this, first I will consider fy at x comma 0. So what is that? By definition, this is limit h tending to 0, f of x plus h 0 minus f of x comma 0 divided by h. I'm not worrying about x. X I am taking as some fixing. Okay. So this will be equal to what? This is equal to what is fx plus h comma 0. So here y is what? Y. So the first for fx plus h comma 0, y term is 0. So if I put in this function, the numerator I will get a multiplication of y is there. So that will be 0. So numerator is totally 0. So this function is getting totally 0, right? So numerator is 0. Then denominator is there. So it is nothing but limit h tending to 0, 0 by h, that is a 0 function. Okay.
Sir, this is not fy, it is fx, no, sir?
Oh, sorry. I have done some mistake. Okay, sorry. Okay. So I will look at, sorry. Yeah, this is, okay. So we wanted to look at fy, sorry. Yeah, correct. So fy means fxh minus f of x 0 divided by h. Okay. Thank you. So this I wanted to look at. So what is f of xh? So that I have to substitute here. So y term is 0. So the second term is turn out to be 0. Only the first term I wanted to look at. So this will be limit h tending to 0. F of xh is what? This is x square h x minus h divided by x square plus h square whole divided by 1h is there, that I will write here. Okay, so this is your term. Then this h and h will cancel. Then the remaining is what? This will be limit h tending to 0 h cube minus h square h divided by x square plus h square. So as h tends to 0, numerator I will get x cube, denominator I will get x square. So this will be nothing but x cube by x square. That is our x. So fy at x0 I got x. So that is a function of x alone. Now if I take a derivative with respect to x, what I will get? So again I am taking derivative with respect to x. So what I will get? So what is my fx fy at 0, 0? Tell me. So my first I have taken partial derivative with respect to y at x comma 0. X is any arbitrary real number. So I am getting that this one as a function of x alone. So I am getting that function is x itself. So again I have to take derivative with respect to x. What should be the value?
1.
1. Yeah. So this will be 1. So this quantity will be 1. Okay. Now you look at again the other one. So you wanted to look at fy at fx at 0 comma y, correct? This is limit h tending to 0 f of h comma y minus f of 0y divided by h. Okay, what is f of h comma y? You have to substitute here. So this will be equal to limit h tending to 0.
Sir?
Yeah, tell me.
Hello?
Any doubt? Any doubt? Yeah, tell me. Yeah, tell me.
Sir,
Yeah,
f of 0 comma y plus h.
Oh, yeah, yes. Sorry.
Yeah, sir.
1 minute.
Hello?
Yeah. 1 minute. This. No. What do you have, son? No. No. You wanted to look at partial derivative with respect to x, right? You wanted to look at partial derivative with respect to x. So 0 plus h will come here. H comma y only. What is the problem? We are looking partial derivative with respect to x. So limit h tends to 0, 0 plus h comma y. That is f of h comma y minus f of 0 y divided by h. What is the problem there?
Okay, sir.
Okay, so somebody else is asking, no? What is that?
Yeah, sir, could you please clarify the thing? Why are you considering the partial derivative of the function at the point x comma 0 or 0 comma y? Like,
so first you want, I will tell you. So while taking derivative with respect to y, we will consider x as a constant, right? So
yes.
After you are taking the derivative with respect to y, and then it will be turn out to be a function of x alone. But evaluating at the point x comma 0. I am looking at x comma 0 only. What actually I wanted to look at a 0, 0 I wanted to look at. Partial derivative with respect to x. First I have to take partial derivative with respect to y. Then I have to take with respect to x. And I wanted to evaluate it at the point 0, 0. So fx, fy at 0, 0, I wanted to look. Yeah. So I will look at
Yes.
fy at x comma 0. So that will turn out to be a function of x alone. Okay. So then I will go for the derivative with respect to x. So all the y term I will, while substituting x comma 0, all the y term will go. I have to take partial derivative with respect to y first. Then I will substitute x comma 0. Then all the y term will go. Because y I am giving 0. Wherever y there, that all term will go. Then only wanted to look at it, that will turn out to be a function of x alone. Then again I will go for the derivative with respect to x. Then I will look at the derivative at the point 0, 0. Total derivative at the point, total thing at the point 0, 0. You understand thing?
Yes.
Is that okay or not? Why I am looking at the point x comma 0 is, first I will look at partial derivative f with respect to y. So I will get a big expression including both x and y. Then I will substitute y equal to 0 there. So all the y term I wanted to gone. Then I only wanted to look at it. Actually, I wanted to look at the derivative at 0, 0. So I will look at along the what actually the partial derivative means. Or if you want more clarity, I can tell what actually the geometry interpret there. Okay. So let us look at here. Just a minute. Suppose you have some object, something like this, some surface. Okay. So you wanted to look at the partial derivative at this point. So what actually you are looking? You will. So you wanted to look at partial derivative with respect to. You wanted to look at this thing. You think fx at x naught y naught. So what actually we will consider is, we will consider some plane. Okay. That plane is nothing but the plane y equal to y naught. So we will look at the plane y equal to y naught, and we will consider the intersection of the three-dimensional object with that y equal to y naught. So here you may get some curve in that intersection. Then we will look at slope of that curve at the point x naught y naught. That is the geometrical interpretation of the partial derivative at x naught y naught. Okay. So here I wanted to look at the double second order partial derivative at the point 0, 0. So what I will look at is, first I will look at the along the line x comma 0. Then I will look at it again taking the derivative with respect to x. Then I will evaluate it at the point 0, 0. So you just don't confuse with things. Here, only thing you need to worry about, first you take the partial derivative with respect to y, and you suppress all the y term. Then you will get a functions along x terms. Then again you take the derivative with respect to x. Then evaluate it at the point 0, 0, where you wanted to look at. That is the method. You understand that?
Yes,
Hello?
sir. Yes, sir.
Yeah. So while doing this, all the y term will go. That is the only thing we wanted to worry. Y term I don't want to there, because because I wanted to evaluate it at the point 0, 0. So first you take the partial derivative with respect to y, then you remove all the y terms, then you differentiate with respect to x. For that I just look at the point x comma 0 first. Okay. So I got fx y at 0, 0 is 1. Similarly, I will go for fx 0 comma y, that is limit h tends to 0, f of h comma y minus f of 0 comma y divided by h. What is f of h comma y? So if I substitute in this equation, it is h square y into h minus y by h square plus y square. H square plus y square. What about f of 0 comma y? That is, if I put x equal to 0, that turn out to be 0 there. So whole divided by h will come. So that a whole divided by h I will just multiply here. Okay. So this h square h will cancel. Then the remaining is limit h tending to 0, h minus y divided by h square plus y square. So what is this? This is again 0, right? Numerator there is a h term. Denominator I will get y square. Since numerator there is a h term, this is getting 0. So what I got? Fx at 0 y is 0. So fx at 0 y is a function of y alone. That function is 0. So what about this one? Then what about this value? Fy fx at 0 y. What you will get? This is again, so because
0.
this 0, yeah, this is again 0. So you got fy fx at 0 0, that is 0. So what about fx fy at 0 0? That is 1. The other one fy fx at 0 0 is 0. So what about the total value? This one, first one is 1 and the second one is 0, right? Second one is 0. So it is 1 minus 0, 1. Is that correct? Is that okay?
Yes, sir.
Yeah. Okay. Now there are similar questions. These kind of questions you can try. Okay. So the same kind of questions what we have discussed here. So here you have to look at partial derivatives, etc. only. I will go for something non-trivial. This is also the same kind of questions. Only you need to worry about fx at partial derivative at 0 0. Okay. Both the partial derivatives. So same kind, whatever we did for these questions, the same method you have to use here. These are all similar kind of questions. I just will go for some non-trivial. Yeah. So you look at these questions. So you wanted to find the directional derivative. So how do you find? What is the directional derivative? So your vector u is what? U is given as 4 by 5, 3 by 5. So you look at whether the given vector is this is the vector. I have written it as in that our notations. So first you have to look at whether this thing is unit vector. So 4 by 5, 3 by 5. So what you get? 4 square by 5 square plus 3 square by 5 square. So this is 16 plus 9 by 25. So that will be 1, correct? So it is a unit vector. If it is not a unit vector, you should make it as a unit vector by dividing the total value. So this thing, okay. So this is a unit vector. Now you look at directional derivative. So that is du of f at 0 0. What is that? Limit t tending to 0, f of tu1 tu2 minus f of 0 0 divided by t. This is the definition, correct? Yeah. So this will be equal to limit t tending to 0, f of t 4 by 5, t 3 by 5 minus f of 0 0 is 0, right? Because that is the case, x square minus y square is equal to 0. Okay, then divided by t. Again, you just substitute the values here. So in the numerator, what you will get? This will be equal to limit t tending to 0, t cube 4 by 5 whole cube plus t cube 3 by 5 whole cube whole divided by t is there, then t square 4 by 5 whole square minus t square 3 by 5 whole square. Okay. So that t cube I can take, t square I can take outside, then it will be equal to limit t tending to 0. T cube in the numerator I can take, t cube from the denominator also I can take. So then the remaining is 4 by 5 whole cube plus 3 by 5 whole cube divided by 4 by 5 square minus 3 by 5 square. So this value you can compute, right? Do you understand?
Yes, sir.
Is that okay? So what is the final value? I will write here. Yeah. Final value I have. Or you can compute directly. Okay, what will be that? You can write it. This is for cube is 64 plus 27 by 5 cube into then in this case whole divided by 16 minus 9 by 5 square. Okay. So this total thing is 91 by 5 cube into 5 square by 8 7, right? Correct. So you're getting 91 by 35. You may cross check this. Okay. So only thing is you just wanted to look at the thing. This formula you have to apply. That is all. Directional derivative of f in the direction of u at 0 0. Limit t tending to 0, f of t u1, t u2 minus f of 0 0 by t. Here u1 is 4 by 5, u2 is 3 by 5. So just put that values here, then you can compute it. So this here t cube you can take outside. Here also t square is term is there. Here t is the total t cube will go. So totally you will get 4 by 5 cube plus 3 by 5 cube divided by 4 by 5 square minus 3 by 5 square. So that you can compute. I think it is 91 by 35. So this also you have seen some examples, the same kind of examples only. You only wanted to find the partial derivatives, continuity. At all you are asking you to find at 0 0. I will look at some other questions. These are also simple questions only. Yeah, can you tell me this? This is all easy questions. I will give you some trick to don't go for directly to compute this, but you can easily get it. Very basic question. Only find the partial derivatives. Directly you have to find the partial derivatives. That's all. You look at fxy here. So in this case, what is fxy? 2 times log of x square y square e raised to y by x. So if you go directly to compute the partial derivative with respect to x and partial derivative with respect to y, it will be tough. So better you use the property of log. So 2 times you can write log of x square plus log of y square plus log of e raised to y by x. So this will giving you 2 times 2 ln x plus 2 ln y plus y by x. That's all, right? Now you can take the partial derivative with respect to x, partial derivative with respect to y. What you will get? Fx is 2 is there, 2 by x plus minus y by x square. And what about fy? Fy is 2 into 2 by y plus 1 by x. So now you wanted to find x fx plus y fy. So x fx plus x. What is x fx plus y fy? That would be once you multiply with the x, so you will get here you have 2 is there, 2 will come, minus y by x will come, again plus 2 is there, 2 will come, plus y by x will come. Then these y by x and this y by x term will cancel. So here we have remaining is 4 plus 4, that is 8.
8.
Yeah, you understand this? Do you understand this question?
Yes,
There
sir.
any doubt? So these kind of questions you don't directly approach these questions. So suppose you can directly also do, but it will be very tough once you go for partial derivative with respect to x directly for these functions. So better you use the property of log and you split it and do this. That is the best thing. And this also you can do the same way. This is also routine computations. You find the partial derivative with respect to x, then you find the partial derivative with respect to y, evaluate it to 1 1. So direct partial derivative you have to find, then you put the value 1 1. Routine computation only. Okay. I will give.
Mahesh, the time is 12 now. You can take maximum 10 minutes.
Okay. Okay. Yeah. Okay, I will do this, or I don't know which one I will do. Okay, then I will do these questions. Okay, this is one CSIR question, not NBHM question. I will do this question. Sorry, not this JAM question. This is a CSIR question. So you just look at this question. This is a little bit different from so what you have seen. So you can observe this and you can tell which one will be correct. So what is the domain here? I just plot here. Okay, I will draw here itself. So you look at the question. F from R2 to R, it is defined by xy is equal to x power integer part of y. Okay. Now the question is whether f is continuous throughout the domain R2, or this function x going to for every y. If you fix one y, you can think as a function x going for f of xy. Is that continuous on some r minus 0? Then another one is for every x in R, this function y going to f of x comma y is continuous on R, or f is continuous at no point of R. So this is the question. So your function is f of xy is equal to x power integer part of y. So I wanted to look at the functions in first I will look at some interval. You look at this is the point 0 and this is 1. So what about the function value? This region, I don't include this boundary. Can someone tell me? I'm not including the boundary. I'm looking all this region. What is the function value? Can someone tell me what is the function value in this region?
1.
1. Why? So in the integral integer part of integer part of y is what? What is the integer? Yeah, integer part of y is 0. So whatever you take f of x comma y will be x power 0 will come. That will be 1. So in this region, function value is 1. Okay. So I will make this as my region D. I may. Okay, this one is I call R1. So on R1, f of xy is 1. Correct? Because x power integer part of y I am looking. What about on R2? I will look at other region as R2. This portion. This is my R2. Okay, here this is 2. I don't including 2, but I will include this 1. I am including this line. Okay, 1. This one I am including. There.
Here is x.
What about the value on function on R2?
X itself.
Yeah, on R2, f of xy is x. So similarly, I can look at each one, right? Other cases, function f of xy is x square and gone. Okay, then you tell me whether this function is continuous on full domain R2. So the next region I will continue this notation. So I will say on R3, this function is on R3, it is f of xy is x square. Okay. So for the next region, I am that region is I will include the point on the line y equal to 2 to open 3. So if you want, I can draw these portions. This side is open, 3 is open, and this portion I will include. So this region I am talking. What about the function value? Tell me. There is x square, right? Because integer part of y is 2 there. Here integer part is 1. Here integer part is 0. So what about the continuity now? What about the continuity on the line x equal to 2? So sorry, y equal to 2. On the line y equal to 2, what will be the function value? So if I take any point from here somewhere, so 1, 2. So this is the point 1, 2 I am taking somewhere here, 1, 2. Okay. So on the 1, 2, your function value is what? What is your function value on 1, 2?
1.
Or you can take it. I don't take 1, 2. I will take 2, 2. That will be fine. Okay, 2, 2. What is your function value on 2, 2?
2.
2, 2. No, not 2. 2, 2. It is 2. Which function you have to use? That belongs to the region R. Yeah, yes. F of 2, 2 is 4. F of 2, 2 is 4. Okay. Now, but what about the region in the left R2? In the R2 region, what about the function value? Or if I look at any line like this, what about the value on that line here? I am looking this line, vertical line. What about the function value on that line? Tell me. On that line. That line belongs to the region R2. So what about the function value on that line?
X itself.
Yeah, function value f of xy is x. So whenever you go very near to this point 2, 2, whatever the small neighborhood you take, that function value will. What about the limit? So I wanted to look at this one. Limit.
2.
Yeah. Yes. Limit xy tending to 2 along that line. I am looking along that line. What I drawn. Okay, line f of xy. What happened to this one? This will be 2, right? Suppose I am looking limit xy tending to 2 along this line. This line, if I am looking along from here, I will get a value as 2, right? Because I am coming from this side.
Yes, sir.
Yeah. So what about the limit at 2 to whether that exists or not? Suppose I am coming from the above. Suppose I am coming from here above along this line. I will get different value, right? Suppose I am coming from here. I will get a different value. If I am coming from here, I will get a 2. If I am coming from here, I will get a 4, right? So along that line, the limit is not existing. So the function is not continuous at the point 2, 2, right? Is that correct or not?
Yes, sir.
Yeah.
Correct.
So the function is so given that f is continuous on R2 is not correct. There are points in which f is not continuous. Correct? Is that okay?
Okay, sir.
So now you look at the second one. You take you fix some y first. Then you look at the function x go into f of x comma y. Is that a continuous function? You fixed some y. You take some y. Then your function is y is fixed. Okay, y fixed. Then your function is f of I can say it is g of x. G of x is the function. What is the g of x? X power y. What about the continuity of this function? This function is from where to?
Continuous.
Yeah, this function from where to?
Continuous.
Yeah, first of all, what is the domain of this function? This function is from where?
R.
Real numbers to positive real numbers.
Yeah, r minus 0 to r. Not, you cannot say positive real numbers. If it is y is some 0, or you cannot say positive real numbers. Suppose integer part is 3. Suppose I take y as some value like y is equal to 3 point something something. I don't know, 3.05 or something. So what about the integral part of y? That is 3, right? Then g of x is x cube you will get. So it takes negative values also. So your function
Okay, sir.
will be r minus 0 to r. Okay, why r minus 0? There may be a things something like this can happen. 0 power 0. It is not defined. Okay, suppose I am not taking r minus 0 instead of r minus 0. If I am taking full r, there is a chance of happening things like 0 power 0. Suppose I take y is equal to some 0.5 and x is equal to 0, then 0 power 0 will come. That is not defined one. So I don't want this kind of things. For that, I'm taking the domain from r minus 0 to r. That is the reason I am taken here r minus 0 as the domain. Do you understand? So each fixed y, if I take, my function is g of x is x power this. So this is a polynomial in x. So some power, it can, some integer value here. So it should be something like x power n. N is the integer. So that happened to be a continuous functions. So I can have a minus 1 also, x power minus 1. So that is turn out to be 1 by x. So that also has to be continuous. So in order to define things well, we have to take r minus 0. Okay. So for every y, this function x going to f of xy is a continuous function on r minus 0. That is the correct statement. You understand that?
Yes,
Hello?
sir.
So what about the third option? Suppose I fix x. X you take some, each x I have to look at. So in this, that will be of the same case, right? What we have told. So suppose I take x is equal to 1. Suppose I take x is equal to 1. Or I can say I don't want to take x equal to 1. Suppose I take x is equal to 2. Okay, x is equal to 2. Then I am looking the function g of y is equal to 2 power integral part of y. That is my function, right? X I have fixed, that is 2. So my function is y going to f of xy. So that function is g of y is 2 power integral part of y. So whenever I look at the domain for y, if it lies from 0 to 1, I will get function as 1, right? This is 1 for y belongs to closed 0 to open 1, and this will be 2 for y belongs to closed 1 to open 2, and so on, right? So this function is not continuous. At one it is not continuous. 1 you are getting, here it is 1 and here it is 2. So at 1 the function is discontinuous. Is that clear? So this third statement is for every x, this function has to be continuous. So function is what? G of y is equal to x power integral part of y. So I fix some x. I take x is equal to 2. So your g of y is 2 power integral part of x. So I wanted to look at whether this function is continuous or not. This function is not a continuous function, because whenever y value lies between close to 0 open 1, I get 1. Whenever y value lies between close to 1 open 2, I get 2, and etc. So this function is not a continuous function. So for x equal to 2 itself, I got it is not continuous. So I don't want to worry about every x, right? I am having some x in which function is not continuous. Is that clear or not?
Yes, sir.
Yes, sir, clear.
Yeah. So what is the option? Only second option is correct. Last option, f is continuous at no point of R2 is wrong. F is continuous somewhere, right? So the second option is correct. Is that okay?
Okay, sir.
Yeah, there are a lot of other examples also. So I will finish here. Already time is 12:16, right? So a lot of questions are there. You just try. These are all direct computations. You can find directional derivative. This is also finding the directional derivative questions. And this is continuity only. Similar kind of questions only. You can try these questions. All are similar kind of questions. So, and I was planning to, if there is time, I was planning to do something called maxima minima also. I have included that notes here. You can just go through this and you can do the problems. I have mentioned some problems, previous year problems from maxima minima also, that you can try, and if you have any doubt you can ask. Okay, I will finish here. That will be fine. Already time is gone.
Okay, thank you, Mahesh. Thank you.
Yeah.
Thank you for the session.
Yeah.
Now, students, you can ask your doubts or you can share your experience and comments. You can unmute your mic and video and you can comment. So feel free to share your experience with us, and also you can ask your doubt if there is anything. Many of them are commenting in the chat box. If feel free to say something about our program and classes. You can unmute your mic and video and you can express your comments.
Sir, class was really effective. This is a wonderful session on multivariable, and I think it will be very much useful for anyone preparing for competitive examination. Thank you, Vinod sir. Thank you, Mahesh sir. Thank you very much.
Okay, thank you, Sanjita. See, നിങ്ങൾക്ക് മലയാളത്തിലും പറയാം, അതുകൊണ്ട് കുഴപ്പമൊന്നുമില്ല കമന്റ്സ് പറയുന്നതിന്. അതുകൊണ്ട് feel free to express your thoughts about our program. Hello?
Hello, sir.
Yes.
Sir, Prachi here from Delhi University. Sir, actually, yesterday was my MSc Entrance exam, And from this topic, function of several variables, I got about 2 to 3 questions. So out of which I could only do one question. Sir, I wish if I could have attended this lecture at least one day before my exam, so I may have attempted all the 3 questions. It would be helpful for me. So that's all. This lecture was really awesome, sir. Your notes were awesome, and they were all very good. I enjoyed it, sir. Thank you.
Okay, thank you, Prachi. This will be useful for your future examinations. Don't worry.
Yes, sir, it will be.
Okay, thank you, Prachi. So, anyone else? See, feel free to express your.
Hello.
Yes.
ഹലോ എൻ്റെ പേര് ശ്രീലക്ഷ്മി. ക്ലാസ് അടിപൊളിയായിരുന്നു. ശരിക്കും എനിക്ക് മൾട്ടി വേരിയബിൾ വലിയ പിടുത്തമില്ലാത്ത സംഭവമായിരുന്നു. പ്രോബ്ലംസ് ഒന്നും ഞാൻ അങ്ങനെ ചെയ്തിട്ടില്ല. പക്ഷെ ഇപ്പൊ അത് ചെയ്യുമ്പോൾ എനിക്ക് നല്ല കോൺഫിഡൻസ് ഉണ്ട്. എനിക്ക് പറ്റും, ഇതൊക്കെ ചെയ്യാൻ പറ്റുന്നൊരു കോൺഫിഡൻസ് കിട്ടിയിട്ടുണ്ട്. താങ്ക് യു സോ മച്ച് സർ.
Okay, thank you.
Okay, thank you, Sri Lakshmi.
Hello, Mahesh sir.
Yeah.
Yes.
സർ, നല്ലൊരു ക്ലാസ് ആയിരുന്നു. സാധാരണ നമ്മൾ ഈ ക്വസ്റ്റ്യൻ മൾട്ടി വേരിയബിൾ എന്നുള്ള ഒരു ക്വസ്റ്റ്യൻ കണ്ടാല് ഈ ടൈപ്പ് ക്വസ്റ്റ്യൻസ് സാറിന് ഡിസ്കസ് ചെയ്ത് ടൈപ്പ് ക്വസ്റ്റ്യൻസ് എല്ലാം കണ്ടാല് സാധാരണ ഇത് ഒഴിവാക്കാൻ പതിവ്. അപ്പോ ഇന്ന് കുറെ ക്വസ്റ്റ്യൻസ് ചെയ്തപ്പോ കുറച്ചും കൂടി മനസ്സിലായി നമുക്കെല്ലാം ചെയ്യാൻ പറ്റും എന്നുള്ളൊരു കോൺഫിഡൻസ് കിട്ടി. പിന്നെ ഒരുപാട് താങ്ക്സ് സർ. താങ്ക് യു സോ മച്ച്.
Okay.
Thank you, Anisha. So I think we can wind up this session now. So the video of this lectures will be available in the YouTube channel of my colleague, Dr. Bijuman. You can search there. You can watch and subscribe that channel for getting the updates. And also today we are having an online examination today at 8 p.m. You can attend there. So thank you all students, and also I use this opportunity to express my gratitude to Mr. Mahesh for being with us for 2 sessions. And I think this functions of several variable portion may be students may find it difficult, and as somebody told in the commenting, many of them are skipping problems from that side. So I think they have get some sort of confidence by attending these lectures, and I am very much thankful to Mahesh for that aspect. So thank you everyone. Let us wind up here.
Okay. Thank you very much. I'm very happy to have a section with the students. Okay. I hope you have got something from my class. If you have any doubts, you can feel free to talk. And I am very.
Somebody in chat box asking to arrange one more session on maxima and minima in that. Okay. Mahesh is also very busy with his research schedule, so we will think about it later.
Okay. So this basically this syllabus is a little bit heavy, because I have seen, okay, whenever you look at as a syllabus, it's okay, it is reasonably okay to discuss, but what I feel is that once you come to the problem side, there are a lot of problems from this maxima minima part, integration part. Those things are there. So if you want to come there, and it will take more time. That is why I have not included that thing in the previous one. And I thought, okay, if I have time, I would have discussed those things today, but I didn't got time also, because while doing problem, it takes times. So I hope you guys can go through that note. I have included that notes in my PDF that I will share to Vinod sir. Then you can.
See, we are having no problem to arrange one more class, but I think you are busy with your research and others. That is why I am not compelling. Okay. So whenever it is
Okay,
possible,
yeah.
you can join with us for one more session. It is for, we can arrange it. Okay, I think whatever number of sessions on this topic, they will be really appreciated by students because they have many doubts in attending problems from functions of several variables and higher dimensions.
Okay.
So
Okay,
we can.
yeah, that we can think now. Anyway, I will share these things to you. That will be better. You can go through that. And I have not done all the problems what I have prepared for the sections. That also I will share. You guys have to work out it, and if you have any doubts, you can contact. There will be no problem for that. You can feel free to contact.
Okay, thank you, Mahesh. Thank you.
Yeah.
So let us wind up here. Thank you, everyone. We will meet again on another day with some other session by some other resource person. Okay, thank you all. All the best. Thank you.
Okay.